In my last video, we talked about frames of reference and things moving. And I titled that Relativity Time is Not a Constant. So here was that was supposed to be the grabber, is time is not a constant. Well, think about the fact that we said that the x value was a little bit different than it was. So it seems like by you're moving real fast and it makes it seem like things are the length is shorter. Length looks a little shorter than it would be. Well, you can kind of believe that. Things are moving fast and from your viewpoint, well, it kind of distorts it and the things like that. Well, what about time? Time, let's see. Well, if the length is shortened, and we've got a yo-yo. Maybe has some effect with time, and we proved it with the math. But I'm just trying to say how do we work that out? So in this video, I'm going to go back over, and I've got a little gizmo here that'll give us a way to calculate how much the length is shortened and how much the time is slowed down in this case. So, how do we go about this final one where the idea is that when you go real fast, your mass increases? What kind of a crazy idea is that? How can that be true? Mass increases. That's the thing that I hope to cover and hope to get you to understand. At least maybe I'm trying to get myself to understand that, is how can mass increase? And is this just something somebody made up? Here's what happened when we went through all that math that concerned stuff that, when we consider the speed of light and all this kind of stuff, this is where we came up with last time. And this is what happened to t. So this is just a repeat of all that. So that's where we were before. Again, the picture's going in the opposite direction as it should. But here's the thing is if we look at these 2 points here, and what I'm going to do is say x1, let me pick the red, x1 prime and x2 prime are this situation. So we get to x2 first, and then we subtract between the two, and this gives us the length. So rather than just with this, this would be the green man that's moving, and this would be the 2 points. Let's just scratch those out right here. These would be the 2 points that occurred between the 2 time periods. So x2 minus x1, that would be a length. If we look at this, then we say x2 minus vt2 and plus vt1. So what are we doing that for? Well, that's because the times for this thing are not the same as the times in the stationary object. Now, to see how much the length changes here, let me just plug in a couple values. Come down here, select that. For velocity, let's say that it is half the speed of sound, 0.5 c. Then we look over at this other one. There's how much the length contracts, 0.8660254, blah, 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 blah. So that's what that happens there. What happens if I get really close to the speed of sound? How much does the length contract? Well, let's take 0.9. Too many points. Let me back up here a little bit. 0.9 times the speed of light. 0.9 times the speed of light. There we go. Now we're about half the length that we were before. And if I add some more nines here, then we're starting to get a really short length. What if I keep going with nines? Starts getting really short. The length gets really short. Now I want you to understand that that length is only what is perceived from this stationary frame. Let me move this thing out of the way so we can see what's going on. So it's only from the fixed frame versus the moving frame. And of course, it all depends on which side you're looking at. Anyway, this you can play around with that and look at the length contraction. The time is going to be reference to the x2 and the x1 in the two times that exist. So there's a bunch of math. You can look at that on your own for this particular one. And let's see for V, let's see what the time is, how much the time is reduced or slowed down if we're going half the speed of light. There, 1 second takes 1.154. Back that up, try the same experiment. There's 0.9. Now it takes 1 second, takes 2 seconds. So you see, it's not a huge slowdown of time, but it's significant. So let's just run this thing out to a whole bunch of nines. 1 second takes 7,071 seconds, so it's moving very slowly. But what was the main topic here? The main topic here was about mass. So, all right, we're back to red man and green man again, and we're going to try to nail down what mass is and why in the heck mass should change as you move. Here we've got the red man with a super telescope. This super telescope can see that green man is making a ball drop in the y direction. Now we won't get gravity involved here. We'll just say he gives it a push and gives that ball what's called momentum. Momentum is, here's P, which represents momentum. That may not make much sense, but that's what they do. And the momentum is the mass times the velocity. I've got these little zeros here because these zeros represent what thing this green man thinks everything is standing still with relationship to the red man, but really the green man's moving at half the velocity of light. Strange, strange, strange. But anyway, what we're going to try to do is say that the momentum from what red man sees in green man's world is going to be equal to the momentum up here. So this we have to believe is that the momentum, whatever is mass times velocity in red man's world, as we see it here, we have to somehow relate to mass and velocity there. Okay, velocity is the change in y with respect to t. In other words, y is changing with time. Now, we chose this in a very specific way because y isn't moving anywhere with relation to red man. So y man or red man, when he sees y go up and down, it's going to be the same as it is for the green man. So the y's and I chose this for that very specific reason. Now, if we look at that, because of that, I say that velocity is the change in y over time, just like it's the change in green man's y over time. And we're going to say that the delta y is equal to delta y over 0, but the delta time is not going to be the same. So we're going to use the relationship for delta time and delta t0 to somehow figure out what's the difference between the m and the m0. All right, some of this should look familiar. Here's the momentum, P. Here's the momentum for green man. This is what red man sees. Here's the momentum. M times V is the same as P there. This is the mass that red man sees. This is the mass that green man sees. This is the velocity that red man sees, and this is the velocity that green man sees. Now, let's take the easy part first. The velocity that red man sees is delta y over delta t, and the velocity that green man sees is delta y sub 0 over delta t sub 0. These are the rest areas that green man sees. Now, delta y and delta y 0 are the same thing, so we can use that interchangeably. Now for the hard part. Delta t as compared to delta t0 looks like this. And this came from some of the other things that we had talked about in the relativity time is not constant thing. Here's the delta t and the delta t0 over this strange square root thing. 1 minus v squared over c squared. Well, what is v? V is what we are moving at, and I put 0.5 c in there, so that is the 0.5 c of the speed of light. So those are squared. So what we need to do is take this v sub 0 and put all these different plug-in things that we have. This v, and plug in all the stuff that we have. The v is delta y over 0. Here's the m. That's the m, well, the mass. That's what we're supposed to be talking about. Here's the delta y 0 over delta t 0. This was the delta t that we had to plug in there, special relativity crap. And there's delta t 0 over, and that's the square root of 1 minus 0.25. Where do you get 0.25? Well, 0.5 squared is 0.25, and then c squared over c squared, those things cancel out, so it's just simple, 1 minus 0.25, square root of that thing. Okay, that equals m sub 0. So these m's, supposedly, according to me, according to Larry the Learner, these m's are supposed to end up being different. Now, how do we figure that out? I'll let you absorb that for just a little bit. Let me go back here and put the brushes on so I can make some changes if we need to. Okay, let's examine these two sides of the equation and see if we can simplify things. We definitely need simplification. Let me go over here and collect a red and get the marker on. Now, I've got a delta y sub 0 on both sides. We got rid of those. Okay, that wasn't too easy, too easy. Now I've got a delta t0 in the denominator on each one of these things. Okay, get rid of that. Now, what is all this? How is this going to relate to getting over to the other side here? Well, that's 1 over 1 over, and so actually this is m times square root of, well, let me just do it to make life easier. Let me actually put the letters to the load here. So if I look at this thing, that's the same as m times square root of 1 minus 0.25 equals m 0. Or, to make everybody happy to the normal way, let me erase some stuff. So I've got room. Well, okay, I don't even need to do that. Let's just take this value, take this equation, and put it up here. Okay, this seems a lot simpler than what we started with. Let's see what the actual results are. Okay, this is going to be mass equals, now this is the mass that red man sees, or this is the mass that red man thinks is going on with green man. So green man's rest mass, oh, I introduced a new term, rest mass, over, I did the calculations in here, and this is 0.866. So what does that make the rest mass? Well, another way to look at that is, what is the reciprocal of 0.866? Let's see if I can do that real quickly here. 0.866, that would be 1.15. Let's just call it that, 3 significant digits. So that would mean that the mass seen by red man would be rest mass times 1.1. Whoops. Let me get that cleaned up here. Rest mass times 1.15. So the mass is a little bit higher. That's at 0.5 times the speed of light. 1.15 greater than the rest mass. So that gives you an idea that until you're very close to the speed of light, things really aren't going to be too much different. But this says that if you get really close to the speed of light, then that rest mass gets really, really large. Okay, let's try our little calculator here for the mass and see what the rest mass difference is. Here, let's plug in 0.5, see if we did our work right. Hey, I think we did the work right, 1.15. Now let's back up and do the same thing, 0.9, and see what the mass is, relativistic mass. Ooh, 2.29. So if I started out with 1 kilogram, now I'd have 2 kilograms once we speed the darn thing up. Now let's put a whole bunch of nines here and let's just see what happens. Oh, now look what the mass is. It's 70,710 kilograms. That's several tons now because we're speeding up way close to the speed of light. Now do you get the idea? I hope so.